the press coverage was a little bit interesting in some cases. So maybe I can clear some things up as well if there was maybe some miscommunications in some of the press. Okay, so you heard my introduction. I do research with radio telescopes, and I look at magnetic fields, and I'm going to talk about both of those things this evening. But I want to start with something very familiar, and I think in the group that I'm speaking to, probably a lot of you have been able to at least at some point gone out into a dark sky and see the Milky Way stretching across the sky. At least I hope you have, because it's pretty spectacular to see it in a really dark sky. And so this is an image of the Milky Way galaxy that I'm showing you right now. Maybe a little bit unfamiliar because this is actually a southern hemisphere image, and so the Milky Way might look upside down to you. So maybe this is a little bit better. This is a northern hemisphere image. And of course, we are inside of the Milky Way galaxy. So it's our home galaxy. Our sun is one of the stars that's inside of the Milky Way. And so that means that we actually see the Milky Way in every direction in the sky. We're embedded in it. And so doesn't matter which direction we look, we're seeing the Milky Way. When we look at this band stretching across the sky, we're seeing the disk, so the thickest part of the galaxy. And over here where we see the big bulge is where we have our galactic center. And so one of the things that I want to tell you about this evening is a little bit of the galactic geography, if you will. So how, how do we talk about the galaxy in context of where we are and our place in it? And how do we describe that? And I think this is something that some of us certainly have thought about, but it's not something that a lot of people think about. It's something that you have to kind of stop and really think about the fact that we're inside of this giant pinwheel in a way. And so as I said, that we're inside this galaxy, the Milky Way, and in every direction we see it. And if we want to take a picture of the entire Milky Way, it means taking a picture of the entire sky and getting rid of the Earth. So we couldn't do that from a single location in a single evening. If you tried to take a picture of the whole entire sky, the Earth would block part of it and it would be in the way, and some of it is inaccessible. So if you take many pictures over a season, you can take a picture of a large part of it. But from our position in Canada, we can't. There's a part that's always blocked. And in particular, it's this part down here. And there's these two objects here, which are other galaxies. So this is the Large Magellanic Cloud and the Small Magellanic Cloud. And there is another galaxy that we in the Northern Hemisphere do get to see. I don't know if anyone can spot it. If you're eagle-eyed, maybe you can spot the Andromeda Galaxy, and it's right there. So that's the Andromeda Galaxy. That's the one that here in the Northern Hemisphere, if we look outside at night, we can see the Andromeda without a telescope. We can see that one with our eyes. And that's the farthest thing that we can see without a telescope. There are many billions of other galaxies in this photograph, but they're not visible unless you have a telescope. So the Andromeda is something that we can see without. And as I said, the Large and Small Magellanic Clouds are also things that we can see without a telescope.
Hey, Jennifer, I'm just going to take a time out here. We've got two other windows on your screen as well right now, a color palette and a no build effects on the screen. So there's something to do with, I guess, your editing of presentations.
That is very strange.
Yeah.
Don't know.
You just may want to
hold on. Let me stop the sharing.
Yeah, they were just covering about 20% of the images.
Oh.
So a color palette in the upper right and a no build effects in the lower right.
Okay. Is that any better?
You'll have to reshare and we can tell you.
Oh, I am sharing. Okay.
No.
Okay, hold on. Hold on. We'll get this sorted.
Okay, so that's the
That's
editing
better.
view. And this is now perfect. Thank
Good.
you.
Okay. I don't know what was going on. All right. So as we look at the Milky Way, the point I'm trying to make here is that we see things at many different distances. So we're seeing these other galaxies that are very far away, but even within our own galaxy, we can have things that are very nearby to us and things that are very, very far away in the same view. So we know that the center of the Milky Way here, the galactic center, is quite far away, and these dark dust clouds are much more nearby. And I'll talk about these dark dust clouds a little bit more in a little bit. So we're seeing this combination of things at all different distances. And so if we really want to understand the geography of our galaxy, we have to talk about distance, and we have to think about how far away things are. And I know as people who go out and look at the sky, often we're seeing stars. And so the stars also are at all different distances. And that actually is information that can really, really help us. But by and large, the stuff that I'm interested in when I look at the sky is gas. And it's not really stuff that we can see with our eyes. In particular, if we want to talk about gas that we see at radio wavelengths. Okay, so I'm talking about geography, so I want to also relate this to the geography of our Earth. And so I'm sure you've all seen a map of the Earth in this kind of projection, which is exactly the same kind of projection that we're seeing the Milky Way in this image here. And so the center is the center of our galaxy, and the center of the map here is the 0, 0 point in this coordinate system, which we call latitude and longitude on the Earth. And our Earth has an equator, and our Earth has a north and a south pole. And so we can define the same kinds of marks on our galaxy. We can define the galactic equator, which is the galactic plane, and the galaxy also has a north and south galactic pole. And so as galactic astronomers, we often talk about how far away things are from the plane and what direction things are towards the galactic poles. So as I mentioned, I am a radio astronomer, and this radio telescope here, which is also the background of my image, is a telescope that is in Canada. It's in Penticton, British Columbia, or close to Penticton at the Dominion Radio Astrophysical Observatory. And this is actually a telescope that I used for some of the images that you're going to see this evening that I used for this research. So this image is not actually from that telescope, but it's from a similar telescope. And this is an image in radio light. So this is what the sky would look like if you could see radio waves. So just like we have different colors of optical wavelengths, red through violet. If we go beyond red, we get infrared, and then we have microwaves, and then we have radio waves, which are low energy, and they're showing us gas in our galaxy that's either kind of cold or that it is emitting by a different mechanism than normal light. So it's actually showing us really energetic particles as well. And one of the things that you might notice is, well, it looks quite a bit different than it does in optical. And we still have a bright galactic center here. And stretching above the galactic center, we have this big arc of emission, which is pretty distinct, and it's kind of hard to miss. So this image is an older image taken a number of decades ago, and we've been observing the sky with radio waves since about, well, the 50s, a little bit earlier, but in the 1960s, we started to make our first really good radio maps of our Milky Way, and that's when we first noticed this feature, which is actually called the North Polar Spur. And the North Polar Spur, as I said, it's really big and obvious. And if you do any radio astronomy and you look at a map like this, it's sort of the first thing you notice. And so when I started doing radio astronomy, I noticed this and I've been thinking about it ever since. And so that was probably 20 years ago now that I first saw a map like this and first started thinking, what is this North Polar Spur? And you might be surprised to know that we don't actually know what it is. And we've been trying to figure it out, ever since the 60s when we first noticed it in the sky. And there's actually two pretty different and competing ideas about what this object is. And I want to talk about both of them this evening. So I'm going to tell you this story about how I came to have my own model of what this object is. So let's go back to our optical image. And as I mentioned, there's these dark patches in the optical image. And these dark patches are dust. And they're dark because they're cooler and they're actually blocking the starlight. So a lot of these dust patches are nearby and they're in the foreground, and the background stars are dimmed as the starlight passes through these dust clouds. So it's just like if you try to observe the sun on a cloudy day, it's a lot dimmer than it is if there are no clouds. And so we see these dark dust clouds in optical images. And you see this one right here is kind of in the same spot where we saw that North Polar Spur, but it's actually not exactly in the same spot. So if I show you another image, this one is in X-rays. The X-ray image shows us the North Polar Spur very, very distinctly. And we also see this dark dust cloud in X-rays. So if I flip between the two images, you can see they're pretty lined up, that dark dust cloud. And so that dark dust cloud is going to figure into the story more as I move along. But in X-rays, as I said, we see this big arc across the sky, and the X-ray images that we have are much more recent than the radio images. And so the X-ray astronomers noticed that this dark dust cloud is blocking some of the X-rays as well. And since the North Polar Spur is shining in X-rays, the conclusion is that the North Polar Spur must be farther away than however far this dark dust cloud is. So that's our first clue as to how far away the North Polar Spur is. Now, there's another clue, and that comes to looking at the sky, not in X-rays, but in gamma rays, which are even more energetic. So X-rays, very energetic, very hot gas. Gamma rays, even more energetic. And if I go back and forth between these two images, you might notice that there's these two bulges that are coming from the galactic center. These were observed with a telescope called Fermi. And so they've become known as the Fermi bubbles. And so these big bulges coming from the galactic center kind of look like the North Polar Spur goes around them and envelops them. And this is a really, I think, a compelling picture. It's very, it looks very much like these Fermi bubbles. The red are related to whatever is happening in the North Polar Spur. And if we look to other galaxies, when we look at other galaxies at radio wavelengths, we see something kind of similar. And this is a galaxy that we would say has an active galactic nucleus. And that means that the central black hole that we find in the center of virtually all spiral galaxies has some kind of outflows. So these jets or bursts of energy that are flowing out from the black hole, and they're emitting radio waves. And so we see many, many galaxies that look like this when we look at the sky in radio waves. And when we look at this picture of our Milky Way, we can't help but think that this might be the same kind of idea that we're seeing. So that we're seeing jets coming from the center of our Milky Way, and that the North Polar Spur is somehow associated with those jets. And as I mentioned, that this dark cloud, this dust is closer to us, and so the North Polar Spur is farther away. And this dust cloud is called the Aquila Rift. And so if I show you kind of picture a diagram, and this is from 2018, these are X-ray astronomers that were looking at these data that made a picture like this. So we have our sun here, and we have this arc of dust that's stretching out. And if we know the distance to this thing called the Aquila Rift, the North Polar Spur must be behind it. And because it looks like it's connected to those Fermi bubbles, and we draw the conclusion that the Fermi bubbles are associated with the galactic center, we, in this picture, say that this North Polar Spur is close to the galactic center, which is quite far away from us. It's about 20,000 light years away. And I'll show you a picture, a more topographical picture of the Milky Way, and kind of explain exactly how far away that is. But is that the right answer? And I said that there's a couple different and very distinct ideas about how far away the North Polar Spur is. The X-ray astronomers have come to the conclusion that it's at the galactic center. But radio astronomers have been looking at it for a long time as well, and have come to a very different conclusion, that it's very, very local. So what is the evidence that the North Polar Spur is local? And this comes from looking at very detailed maps of dust and also gas. So these two maps here are looking at a very detailed map of dust, and I'll tell you how this map is made in a moment. And this map is the gas, which is also made by observing radio waves. So this is cold hydrogen gas that's existing in its neutral state. So it's so cold that it usually hydrogen breaks apart and becomes, and it glows like the fancy pink H2 regions or ionized gas regions that you see around stars like the Orion Nebula. But if the gas is much, much colder, it becomes neutral, and we can only see that gas when we look in radio waves. And if you compare this map to what we've been looking at, you can kind of see that this area here looks like it's where the Aquila Rift is. And if you look at this up here, this is coincident with the North Polar Spur. So we're seeing cold gas that's associated with the North Polar Spur, and we're also seeing dust that's associated with the North Polar Spur. Now, I've been focused very much on the North Polar Spur, but there's also this really bright patch over here, and this is our galactic plane. But this patch looks really bright and a little bit above the galactic plane, and this patch is called the fan region. So the fan region is going to play into our puzzle in a little bit. I just wanted to point it out right now. Okay, so why do radio astronomers think that the North Polar Spur is nearby? And one of the really big clues comes from the dust. And that dust map I showed you actually wasn't an actual photograph. It was made by using this map, which I've been showing you several times now. This is actually not a photograph. This is made from a telescope called Gaia, which maybe you've seen some stories about Gaia in the news recently. And Gaia is a satellite that has done very, very detailed survey of every single star in the sky. And in particular, Gaia has concentrated on measuring the position and brightness of every star very precisely. And one of the things that we can do by measuring the precise position of a star is we can measure its distance. And this is by using this idea of parallax. So parallax is the idea that if you have something nearby and you're observing it against a much more distant background, the nearby object is going to appear to move against the background if your position of observing is changing. And because we're observing from the Earth or from a satellite that's in orbit around the Earth, and the Earth is going around the sun, the position in space of the Earth is changing. And so a nearby star, like the stars in the Pleiades, would appear to shift against the background of much more distant stars. And if we measure that amount of shift, we can very accurately measure the distance to that nearby star. And so that's what Gaia has done for over 1 billion stars in the sky. So this orange circle in the middle says that Gaia has measured the parallax and the proper motion, which is just the real motion of the star in the sky, for 1.3 billion stars. And this is the best and most complete sample of stellar distances that we've ever made in the history of astronomy. And by measuring the distance to those stars, and we can also look at the star and we can get a measure of the amount of dust that's in between us and that star. And we do that by looking very closely at the color of the star. So we can see that stars are different colors. And as I pointed out, the stars that are behind the dust cloud, they're dimmed by the dust cloud. And so we can measure the amount of dimming, and we can measure its position very precisely. And through all these measurements, we can make a three-dimensional picture of dust in space. And that's what this little animation is right here. This is recent work that has measured very precisely the distance and the position of the dust that's between us and the stars. And we can measure those distances so precisely because we know the distance to those stars. So this is a box in our very nearby neighborhood. This box is about 1,000 light years. I'll show you how big that is in just a moment. But you can see that there's two sort of walls of dust, and in between there's a kind of an empty region, and it's coming around just a second. So here is this empty region in between these two walls of dust. And this is something that's called the local bubble. And so that local bubble is that void that's in the middle between these two walls of dust. So I said that box that I was just showing you was about 1,000 light years on the side. This is our Milky Way as it would look if we could get in a spaceship and fly out into space and look down on it from the top. So here is our position, the sun's position in the Milky Way, out in one of the spiral arms. The Milky Way is about 100,000 light years across, and that box is 1,000 light years. So the size of that box is about like that. So this is a very, very local region around our sun where we're measuring the distance to all that dust. And if you recall this image, this is an image of the dust in a very nearby region. It's going a little bit farther than the 1,000 light years, but we see dust associated with the North Polar Spur, which is telling us, again, another clue that the North Polar Spur is closer to us than the galactic center, because the galactic center is way out here. As I said, this is about 20,000 light years, and this is only 1,000. And so if we're seeing dust in this very nearby neighborhood that's associated with the North Polar Spur and with the Van region, then it's telling us that the North Polar Spur must be much more nearby. And this Aquila Rift that I told you about is actually in this image of the dust. It's part of one of these walls of dust. So we have a bit of a puzzle, because there's some pieces of evidence that's telling us the North Polar Spur is actually closer than the Aquila Rift. And then there's other kinds of evidence that's telling us that it's farther away. So we have we have a mystery on our hands as to how that object can satisfy both of those criteria. Okay, so that was a bit about this contradiction, and we don't exactly know how far away this North Polar Spur is. And so my part of the story is coming up, but first I want to give you a little bit of a feel for how I study magnetic fields in space. Because as I said in the introduction, that's one of the things that my research really focuses on. And so what is this all about? How do we look at magnetic fields, and what does this mean? Well, if I ask you to, what is a magnetic field, or where have you encountered magnets before in your everyday life? You might say that you have magnets on your refrigerator. And if you take a magnet that you put on your refrigerator, maybe you've done this in school at some point in your life, if you take that magnet and you put a piece of paper on top, and then you put little iron filings on top of that, the iron filings will organize themselves in this pattern, which is reflecting something that we call the magnetic field. And so what is that? Well, it's producing forces that are pushing those pieces of iron around and making them align in this pattern. Another place that we might have heard about magnetic fields is in the context of our sun and our Earth. Our sun and our Earth both have magnetic fields. This is responsible for us seeing the northern lights, the aurora. And I really love this image of the sun. This is energetic particles that are being flung out from the surface of the sun. And in this image, you can actually see these rope-like structures, these prominences, but they're actually forming these lines, which is reflecting the magnetic field of the sun. So it's very similar to the idea of the iron filings on the magnet. They're charged particles that are flowing along the magnetic field lines. So we maybe have a little bit of an idea of what magnetic fields are. How do we measure them, and how do we look at them? And what does this have to do with looking at radio light? Well, one of the ways that we do this, in fact, the primary way, is through this phenomenon called polarization. And you might have encountered polarization at some point, especially if you wear sunglasses. You can get polarized sunglasses. And polarized sunglasses work something like this, where if you have light from the sun, for example, or another unpolarized source of light, and the light is traveling in waves, and the waves are all jumbled up, and they're all in different orientations, and you put a polarizing filter in the way of that light, it only lets light through that has a particular orientation or is polarized. This light that's coming out on the other end, we say that it's polarized. And so with astronomical objects, we can get something similar, a similar effect that happens because of magnetic fields. So here we have a star. That star is not polarized. If it passes through a region of space that has a magnetic field, in that magnetic field, we have little grains of dust, which, like the iron filings, align along the magnetic field lines. And this acts as a polarizing filter for this light from the star, and out the other end, the light emerges as polarized. And we can actually measure the orientation of this polarized light by changing the orientation of the filter on our telescope. And where it's brightest, we know that that's the orientation that the light is polarized. And in doing so, we're actually directly being able to measure the orientation of the magnetic field. So it's pretty cool. It's actually a relatively simple kind of measurement at its on a fundamental level, but it gives us this really powerful information about our universe and our galaxy. So the Planck Observatory is another space telescope that has observed polarized light. And this is a map that you can make by measuring the orientation of the polarized light in space. And this is polarized light that's coming from dust. We can also measure a different kind of polarized light, and this is something called synchrotron radiation. Now, I won't talk a lot about what exactly this is, but this map comes from dust, and this kind of light actually doesn't come from the dust, but it comes from the energetic particles themselves. And so we can make a map that comes from the energetic particles themselves, and it looks very similar to the one that comes from dust, but they're not identical. So if I flip back and forth, you can see that there's some similarities, but also a lot of differences as well. And so this is telling us where the energetic particles are in space, and this is telling us where the dust is in space. And by comparing them, we can know where we have both things happening in the same spot. And once again, I'll point out that the North Polar Spur, the North Polar Spur is visible in both the dust and in the energetic particles. Okay, so how do we use this to tell us whether the North Polar Spur is close to us or far away? And the answer is, once again, stars. So we can also measure the polarization of the stars themselves. And all of these little black hash marks are measurements of an individual star, whereas the background is the measurement of the dust. And you can see that in this example, the stars and the dust align pretty well. And what does that tell us? Well, it tells us they're in the same place. And if we can measure the distance to the stars, then we can also measure the distance to the dust using this method. So let's look at our North Polar Spur. Now, this image is actually showing the North Polar Spur all the way across the image. So it's kind of a zoomed in patch that's just showing us the top and the bottom part of the North Polar Spur. And so let's look at this top part, the part on the right first. So the red hash marks are the orientation of polarized light coming from the energetic particles from the synchrotron. And the yellow is the polarized light that's coming from stars. And if you look up here at the top part of the North Polar Spur, you can kind of see, maybe you can see that the little hashes kind of line up. And so the yellow ones and the red ones, they are oriented in the same way. And so if we can measure the distance to the yellow ones, then we can, we can infer that the red, the light that's making the red ones is at the same distance. And it turns out the stars that are making the yellow ones, in this case, are very, very nearby. So that's telling us that the red stuff, the red lines, are also nearby. So we know that the energetic particles making the North Polar Spur shine in radio waves, and the yellow, which is the stars, are at the same distance, and the stars are very nearby. And when I say very nearby, I'm talking about less than 1,000 light years, so just a few hundred light years away. Now, this is really in contrast to the X-ray picture that put the North Polar Spur at the galactic center. And so this evidence tells us that it can't be that far away. It has to be much more nearby. But over here on the left-hand side, this is the bottom part of the North Polar Spur. Remember that part that was behind that dust cloud called the Aquila Rift. And in this part, the yellow and the red don't line up at all. So they are in totally different directions. And so this tells us that the stars, which are nearby, and the energetic particles have to be at different distances. And in particular, the North Polar Spur emission here has to be far away. So again, we have this puzzle. We have different observations that keep telling us that this part of the North Polar Spur at the bottom has to be far away. But there's lots of really strong evidence that says this part has to be nearby. So if we're here in the sun, how do we get a picture where this is far away, but this part is nearby? I could let you think about that for just a few seconds. Now, maybe it might work if you pulled this part of the North Polar Spur down. And remember that we live in 3-dimensional space. So this doesn't actually have to stick straight up above the galactic plane. It can actually stretch overhead over top of the sun, and it will look similar. And so this is where the research that I've done is starting to present this picture of a North Polar Spur that doesn't stick straight up above the galactic plane, but something that is parallel to the galactic plane and stretches overhead. So I want to tell you about how I sort of came up with this, and it wasn't through the way that I've just explained it to you. It's only in hindsight that I'm able to go back and see that it really makes sense. But it came from staring at these maps, these radio maps. And this one, I said, is an old map that we've had for a long time. A map that we haven't had for a long time is one that looks at the polarized version of this radio light. And when we see polarized radio light, it looks quite different. It looks like this. And this is the map that was made with that telescope that's behind me in the background, the one at DRAO. So I was staring at this map, and I was actually at a conference, and someone mentioned that in an offhand way, they said that the Antarctic plateau of this map, referring to the position of where Antarctica is on a map of the Earth. And so if you look at a map of the Earth and you see Antarctica, you see that it looks really stretched out and it looks really big. But you might know that Antarctica is really not that big, because it only is appearing that way because of the way that we're looking at the map. That the way that we've represented this 3-dimensional sphere on a 2-dimensional surface. And if we actually change the position, the center of our map, we can get a better picture of what Antarctica really looks like and see that it actually looks kind of small. And I think this is coming into play for astronomers as well, because astronomers always like to make this map with the galactic center in the middle, and it distorts our view of the way we see the sky. And so I wondered what the map would look like if, instead of centering it on the galactic center, instead we put the center up here in between the North Polar Spur and the fan region. Because I noticed that these two objects in this map, they look similar. They're both quite bright in the polarized radio waves, when the rest of the map is not that bright in this particular way of looking at the sky. And so when I made a new map with that red cross at the center, what we get is something that looks like this. And suddenly the North Polar Spur no longer looks like it's arcing above the galactic center, which is here. And instead, it looks like it could actually be parallel to this patch that we call the fan region. Now, another thing that happens somewhat coincidentally and around the same time is that somebody I know pointed out this paper to me, which was from 1965. And in that paper, there's a mention of the North Polar Spur and the fan region, which were just discovered at that time. And they made a comment that maybe that they're due to us being embedded in the local arm of our galaxy. And so this is, again, a map of our galaxy. This is the local arm. So the sun is here, and this is the arm that we are in, the spiral arm where we're located inside the galaxy. And the local arm has an orientation of about 70 degrees on the sky. So if you point towards the galactic center and that's your 0, then this angle here is about 70 degrees. So, my thought was, well, what happens if we are embedded in this local arm and we have a magnetic field that's parallel to this arm, And what would the sky look like? So I just asked this question and made a really simple model. And so here is a top-down view of this really simple model that I constructed. And so we have to look at this in 3 dimensions. So you have to imagine yourself in the middle, and you actually have three bands going overhead, kind of like if 3 airplanes were to fly overhead and leave contrails behind. And then you have 3 of them below your feet and 1 on either side of you. So I actually have a 3-dimensional drawing that I attempted to do that shows this. And so we're the red dot in the middle. So if you imagine that you're standing there and you look above and there's 3 lines going overhead and there's 3 going below your feet, and then there's 1 on either side of you, what would that look like if we were in this box? And it turns out it looks like this, which kind of reminds me of what we see as the North Polar Spur and this big bright patch called the fan region. So I did played with this model a little bit. I changed the orientation of the lines, and then I removed some of the lines, and we get something that looks even more like what we see in the actual sky. So this image that I'm showing here is another radio image from a different radio telescope that's also showing us the polarized radio light. Now, you can see that there's a discrepancy here down at the bottom, doesn't look the same at all. And so the last modification I made to this model was, instead of having straight lines, I made lines that were curved. And these curved lines give us a picture that is shown by these white outlines. So I'm showing this on top of a radio map. And suddenly we have a picture where we're able to reproduce the location and the orientation of the bright features that we see in the radio sky with a really super simple model, just of 4 lines that are stretching above our head and beside us and below our feet in the sky in a 3-dimensional space. And so these lines, they're not actual lines. What they are is just regions in space that have more gas than the rest of the regions. And the magnetic field is stronger in those places. And so they shine more brightly in radio waves. So what does this look like on our map of the galaxy? Well, these little orange lines here, you can see, are these filaments that make up this model. Now, one of the really cool aspects of this model is, remember that picture of the North Polar Spur being far away and sticking up into straight above the galactic plane. Well, in this picture, it's not straight up, it's more parallel to the galactic plane. But we still have the case where this pink blob here is due to that dust cloud, which is the Aquila rift that we see as that dark splotch in the optical image. And so in this picture, this line can actually both be very far away and nearby at the same time. And so this picture is able to solve that mystery that has been around for a long time on how we can have an object that's both far away and nearby all at once. You can have that if you have a very long object that is stretching far away into the distance. Now, I want to just for the last couple minutes here, just talk one last time about this fan region, because I've kind of been ignoring it and spending a lot of time talking about the North Polar Spur. Now, the fan region, you might wonder, why is it called the fan region? And the reason is from this observation. This is from 1964. And this is a picture of polarized radio light that was taken with the telescope back in the 60s. And again, remember the picture of the iron filings on the magnet. This is tracing the polarized light in the sky using the orientation of the way where the light is most highly polarized. And if we look towards the fan region, the orientation of the polarized light looks like a fan. It diverges and is kind of straight up through the middle. And so the other cool aspect of this model that I developed is it can also explain the shape of the fan region. And that is because polarized light has this property that as it passes through magnetized gas, the orientation actually gets rotated. And this is a process called Faraday rotation. And this process depends on whether the magnetic field is pointing towards you or away from you. So if it's pointing towards you, it gets rotated one way. And if it's pointing away from you, it gets rotated the other way. And so if you look at this picture I have again of this model, the magnetic field is running along this line. And if you imagine our position here at the sun, if you're looking at the magnetic field over here, it's coming towards you. And if you're looking at over here, it's going away from you. And so this is showing the Faraday rotation from two cases of the magnetic field going away and coming towards you. And so that on this side, the magnetic field is going towards you. On that side, it's going away from you. And we can make a model of what this would look like. And it turns out it looks just like a fan. And so it looks very similar to the fan region. So this really simple model that's just 4 lines of magnetized gas in space can explain a whole range of observations, and it really makes a nice coherent picture. The one thing that is sort of missing from this picture is those Fermi bubbles, and that still remains a mystery. So what I think is that the Fermi bubbles are probably unrelated to the North Polar Spur, and it's just a coincidence that they're both the same direction in space. But this is the actual picture that went into the publication. And this picture, when I sat here and stared at it, I thought, it really kind of reminds me of a curving tunnel. And so I got the idea that if you had lines drawn on a tunnel that was curving and you were inside of it, that you would see this kind of picture. And so that's where this image came from that went into the press release. And for this press release, I made this version of the image, which was, what would the sky look like if we were actually, observing, if we could see the magnetic field lines and we could see radial light, how would this look like in the sky? And what I made this image, it even surprised myself as to how much it resembles this curving tunnel. Because on here, these, once again, we're able with the radio to find the orientation of the polarized light, and it follows along these lines. And so this is the origin of this magnetic tunnel and why I call it the magnetic tunnel. It's actually not so much a tunnel, but it's us being embedded in a spiral arm of our galaxy, and that spiral arm has magnetic field lines and has gas in it, and we're inside of it and seeing it from the inside. And this is actually really close to us within the geography of our galaxy. So it's much closer than the galactic center, which is over here and not visible in this image. And so I'll just leave you with this map that I made showing the position of the constellations. And so if you go outside at night and you can find these constellations, which are all bright, well, lots of bright constellations that are easy to see from anywhere in Canada, and you can imagine that we could see radial light. This is where these different parts of the radio picture would be in the sky. So that North Polar Spur is stretching through Boötes, through Corona Borealis and Hercules. So if you find those constellations in the sky, you can imagine that that is along one branch of this magnetic tunnel. And on the other side, through Cassiopeia and Cepheus, is the other side, and down through Cygnus and through the middle of the Summer Triangle is where where the barrel of our local arm is in space. And that is where I'm going to leave it, and I'm very happy to answer any questions that you might have.
Wonderful. Wow. That certainly explains a lot. Does anybody have any questions? Mark, I think you would ask a question in the chat.
Mark K.
Yes. Okay. He wanted to know what the dark spots were. When you actually showed the plane, there were some dark spots in there.
In the first 3 or 4 or 5 slides.
Yeah. Right near the beginning.
Like these dark spots or something else?
We don't know because Mark's not here.
You leave?
Well, we can come back to that. No, he's still
It was
here he is.
later on.
Try to decide what image it is. It was the one that was green.
The one that was green. This one.
Yes.
Okay. So like these dark spots.
No, in the
Across the middle.
plane, there's some very obvious dark spots.
Oh, these ones. These ones.
Yes.
Okay. That's a good question. I think they're actually missing pixels. Actually, you know what those are? I'm pretty sure those are actually shouldn't be, well, in real life, they're extremely bright radio sources. So they've basically been masked out. So it's like if you're doing an optical image and you're in, a super bright star, it can
Overloads the
overwhelm.
detector.
Yeah, exactly. It can saturate your detector. And so I think those are actually blanked out spots because they're in areas that are really bright radio sources.
Okay, thank you.
Yeah.
So I have a question. There was a new radio picture that came out not too long ago. Have you tried, putting that image on top of this to see if you can find the loop?
In fact, that was I almost put that image in this talk and I never got around to it. That image is actually right in the galactic center. And so it's a very high resolution image of the very middle of our galaxy.
Mm-hmm.
So it's not directly related to this bubble, like in actual space, it's looking at the very galactic center, and then my tunnel is right over here.
Mm-hmm.
But the reason I wanted to include that is that you see these filaments that stretch up from the galactic plane. And so those filaments, I think, might be analogous to the structure that we're actually seeing around us. Like I've often been asked, what are these lines actually? And they're compressed dense gas. And I think that those lines that you see in that image of the galactic center are similar compressed dense gas that are glowing in radio waves.
Okay, excellent. Thank you. It is quite the image though.
It is. It's beautiful. Yeah, I know. I really need to stick it in this talk.
Okay. Does anybody else have any questions? Unmute yourself and ask away. No, is okay. Well, Jennifer, thank you so much. This was fantastic. I enjoyed it. And I mean, those pictures look like, as Mark was saying, Van Gogh paintings. They are just amazing. I'm just sitting here thinking, wow, I could start doing watercolors on those. Those would be really great. But okay, great. Thank you so much. And I think we're going to just carry on. I'm not sure whether David Levy has shown up yet. No, he's not here yet. Oh, can we get a copy of the last image? So I think Peggy wants to paint it too.
Oh, you mean you mean,
Yes, the one with the constellations on it.
Yeah,
yeah, absolutely. I can send it. I'll send it to Kim or something.
Sure.
And then
that'd be great. That'd be awesome.
Thank you.
Thank you. Thank you. Okay. I'm going to carry on here, and I added a few things. So David's not here right now. And I wanted to add in John Hurley. Did you have any updates from the national office?
No, there's no updates. There's
Okay.
that apology letter that was issued by our president almost a month ago. I hope everybody's had a chance to read that. And if they have any feedback to give national, please do so.
Okay. Thank you. And Susan, you have an announcement?
I am your Fallen Stars 2022 chair because Kingston is the lead this year. And so Steve Barnes has let us know that he's able to secure the same campground at South Bay for us. And the date that's available for us is the 23rd, 24th, and 25th of September this year. So we had some pretty nice skies last year, and things can only improve. And I'll be looking for ideas for whether people want to run the Saturday sessions as how-tos. If you want to have a speaker, just let me know what ideas you have about that. And as things firm up, we will post the dates and everything on the website. That's it for now.
Okay, great. Thank you, Susan. So now we're going to carry on with Hank Bartlett and Hank Sunspot.
Oh, that's me. Okay. And there we go. And here we go. There we are. Welcome to Hank's Sunspot for January 13th to February 8th. I shortened it by a day because I got tired of trying to rush on the last day, the meeting day. So now it's done as of yesterday. So here we are. It's been a real decent month, that's for sure. Quite enjoyed it. Could have used a little more clear sky, but things have been well. And on the bottom of the screen here, you can see the X-ray results from the 4 M-class flares we had during the month, the M1.8, 1.5, 5.5, which was getting up there. We're going to get a next flare soon. And the M1.1. Unfortunately, none of these flares gave us any decent aurora or really any aurora at all. I currently have a friend living in northern Manitoba, not that far, maybe a few hundred kilometers from Churchill, and they really didn't get much of anything there either. So we're not losing out that much, but they did at least have something. On this is a very too many images. I had a lot of problems early in the month or in the latter part of January. I've been playing around with the Edelon and trying to get better resolution than that, but it hasn't been working too well. It's really tough sometimes getting the shift just right so that you see the most amount of surface and the most amount of prominence. But anyway, this one's a white light. January 14th had its highest number for the month of sunspots in one day, sunspot groups, which was 8 of them appearing on the same day. And the amount of sunspots that are Earth-side bigger have greatly increased for sure in the past month. The C flare is now surpassing 100. It's actually considerably over 100 for this month in particular. And things are really looking up and out, and very happy about that. Now, solar activity did take a little break, and as it always will, regardless whether we're having a maximum or not, there are times when it just slows right down, but it slows right down at a much higher level. And here you see it just reaching down just to the almost 10 to the minus 7 X-ray count. But in the low periods, we're in the solar minimum, we're down to 10 to the minus 9. So 10 to the minus 7 is quite passable, love it, and still a few spurs there. It only took a couple of days and it's picked back up. It lasted about 3.5 days. And then activity increased, and this is a week later, thereabouts. And we've got, oops, just moving something. Yeah, about a week later. And we've got a lot of activity. You can see there, a lot of C flares going on, very small grade, a lot of them, but with the baseline flying right along the sea level, you can't help but get some good C flare activity. Now, 2 of these C flares were caught by Kim Hay on the 28th of January. And you see here on the left, a C 1.1 and a C 3.1 on the right in AR 2936. It's always great to be out there at a maximum of any kind of flare and catch the imaging. I was not that lucky. I did not catch any maximums at all. And on this particular day, the C flares ranged from 1 to 3.1, and overall 2936 was credited with 54 C flares this past meeting month and 2 M flares. So it was a very active region, and the more of those come along, the happier Hank and Kim will be for sure, and a lot of other solar observers. Then came along this beautiful prominence on February 3rd. This started to form as a very long hedgerow along the surface, and on the 4th, 5th, 6th, 7th, it got nothing but better and better until the 8th when it did collapse. But these are 3 images, and these are 3 sets on the 5th, the 6th, and the 7th. And the amount of change in the prominence was amazing. And in this center one here, in the whole size image, especially the full sun, the way it's shaped and everything, I thought that's got to be something wrong with that. It's just not right. It's too defined, too shaped and bordered around the edge. And I thought I've just got either really poor imaging or did not process it properly. But then I looked back to the gong images, and they were basically the same thing. This almost like a fishnet or something thrown out, as opposed to on the left and on the right, it was this big smoky kind of flowery kind of thing that drifted out into space. But this was something was going on there. Who knows what? Now you can see also that during that time, this central part, what it was by the looks of it, if you look on the left, this one spire, the right-hand spire, it almost looks to me like it took control of this whole thing. And the left-hand one collapsed and this right one burst out. And then in the right-hand image, that spread and started to drift more again. So whether it's a point of magnetic fields expanding and contracting, I don't know the science of it. I don't know anybody that does, but you can definitely see, like I say, over these 3 images, the amount of change that has gone on. And during that few days. Now, on the 8th, it collapsed. Wow, Australia was getting their good view of it. This is a view from the SDO. This is the camera we'd all like to have, that's for sure. Anything like this would be just phenomenal. This is over hours and hours that this is taking place. And would love to, I am not in the range of equipment or anything to catch these long exposures or movies, but this is absolutely fantastic. And if you look for the GOES image, it comes out even bigger towards this picture of the SDO satellite. It comes way out into space here as well. So it's worth going and looking. Go to spaceweather.com. Unfortunately, one of the things I wish they would do with the gong images is if they were able to expand the cropping that they do of the image, or I guess it's maybe just the telescopic maximum, the size of it, because these cut off right about this area, a very narrow margin around maybe 50 to 75,000 kilometers around the edge. Sometimes it's not that good, but anyway, that's basically what the month has been as far as images. This meeting month, we had 20 active regions from 2924 to 2943, and X flares were 0. We're looking forward to this month. M flares 4, C flares 148, for a total of 152 flares. So the 2936 did over 1/3 of the amount of flares itself. And for the Raw Observatory, the imaging sessions were 14 for the month. I'm looking forward to being in the 20s this next month, as hopefully weather settles a little bit and gets a little more clear sky. But that is it for this month, and thank you for watching. And that's it.
Thank you, Hank.
Thank you.
That is phenomenal. There is a fellow on one of the other solar astronomy lists that ended up catching that prominence before it fell.
Oh, really?
And just jaw dropping, just drama. Yeah.
That would be excellent. I looked at different movies. The only one that had really good movie was Australia. If you could patch them all together, maybe it'd be okay. But if you go to Gong H Alpha, you can, if you click on the play button, then it'll bring up the daily video. But at the top, you can change the dates and go back to the day that it happened, and watch these movies and speed them up, slow them down, take them frame by frame, whatever. If you're at all interested in solar, it is well worth doing that.
Thank you. Thank you again. And let's hope for some clear skies, because I want to try out a few more things. Yep. Okay. Thank you. Okay, next we're going to have Rick Wagner and what's up in the sky for February.
Well, good evening. I'm afraid it's a little bit of a, however, make do with what we get. Local events here. Queen's University has started up their routine Friday colloquia. Now at 1:30, I think they used to be at 2 o'clock in the afternoon. But anyway, Rachel Friesen from the U of T is going to be talking about the Green Bank ammonia survey, looking for gas in the galaxy. The Queen's University Observatory continues producing fast radio burst podcasts. That's Nick Aurora and Connor Stone. They've added one on our lonely galaxy. And after, I think 4 or maybe even 5 now, they've had on a series of the sort of the destructive universe, the dangerous universe, ends of the universe, all that kind of stuff. They've decided to start going a little more positive looking, and they've got one called The Living Universe. The Paradox, of course, that's the Fermi paradox, that if there's all this life out in the galaxy, why aren't we seeing any of it? And they predict that's going to be the first of probably 3 episodes on life. The BAA is having some events on the 16th of February, a webinar on all things all sky. I'm not sure exactly what that means. Maybe it's something like what I'm doing now. 5th of March, the Deep Sky section is having their annual meeting. For any deep sky observers, that might be interesting. AVSO webinars on the 26th of February. They're having their members only presentation by Dr. Margarita Karowska on variable stars and interacting binary systems in high definition. So that'll be interesting. And then the next open how-to hour, open to the public, they haven't decided on a topic yet. So, and those are all Saturday afternoons at 2 o'clock. Hours of darkness for the coming month or so. I've rearranged things a little bit here. I think looks a little more readable. So you can see that over the next 20 days or so, sunset gets about almost a half an hour later. We're losing our night. Sunrise also half an hour earlier. And the altitude of the sun goes from 31 degrees up to 39. So the seeing will be getting much better for the solar people. Up in the sky for February. This evening, unfortunately, as Kim mentioned, it was raining when I came out to the office. So nobody will have seen the eyes of Clavius. I'm not even going to tell you what those are, except that they appear, I think it's about 24 or 26 hours after the lunar X. So you can keep a lookout for those. I'll try and keep predicting when they're supposed to occur, and people can just go and find out what they are. For the coming week, Mercury is visible because of the shape of its orbit and its the tilt relative to the ecliptic and stuff. I think it's actually at greatest elongation east in about a week. But because of the tilt and everything, it's actually most visible right now and getting less visible through the week. So it's a good time to get out and look for it. I'm going to keep pushing the Algol minima. 11th of February, there's a late one, I think 11:30 at night or something in the evening. So you'll be able to watch Algol decreasing towards minimum. On the 12th of February, Venus is at greatest illuminated extent, which means the total illuminated surface area visible from the Earth is at its maximum. And so, of course, that also means it's at its brightest at a stunning minus 4.9 magnitude. You won't miss it. 13th of February, Venus will be 7 degrees north of Mars. Mars, I think, at about 1.5 magnitude, so over 100 times fainter than Venus. And 7 degrees is far enough away that Venus is not going to be that great a pointer to it. 14th of February, an 8 p.m. Minimum of Algol. So nicely timed to catch much of the descent after dark falls and then catch it coming back out of the minimum towards midnight. 16th of February, full moon. 23rd of February, last quarter moon. And the 27th and 28th of February, all the planets are moving into the dawn sky. So we have a chance to see the moon, Saturn, Mercury, Mars, and Venus all together in the dawn sky. The moon will be a thin crescent. Saturn will be quite difficult because it'll still be fairly close to the sun and not very bright. I think Mercury probably will be difficult as well. So you'll probably need binoculars to pull them in. And then a few things in early March before our next meeting, the 2nd of March, Mercury will be 0.7 degrees south of Saturn. New moon at just after noon on the 2nd. 5th of March, Jupiter is in conjunction with the sun. And of course, we won't be observing that, but it's good to know that it's coming around and that represents the beginning of the next much better apparition. this is going to be an excellent apparition this year. It's going to be much higher in the sky, and I think the closest it's been in 70 years. And 6th of March, another algal minimum about 10 p.m. in the evening. So 2 comets in the sky that neither of them are very bright, but possibly of interest. Comet 67P Churyumov-Gerasimenko. You can see here, this is a plot. The little thin line in the center is its path through the month. So moving south, and as we come up to our next meeting, you can see it goes past fairly close to a pair of about 13th magnitude galaxies. So that might make a nice picture. And it's running around 13th magnitude itself. And the other comet of interest is 2019 L3 Atlas. Here again is its path over the coming month in the feet of Gemini. So it's about 12 to 12.5 magnitude. So again, still fairly faint. In the world of asteroids, number 4, Vesta, will be in a perfect straight line between Venus and Mars on the 26th, the morning of the 26th of February, about 2/3 of the way from Venus to Mars. And it's about 7.5 magnitude, I think. So that's something that with a pair of binoculars or a small scope, you should be able to give you a good pointer to find Vesta. And oddly, this month, there are no predicted asteroid occultations for our area. So maybe next month. And that's all I have.
Hey, thank you, Rick. That's awesome. I know a couple of our members have been very busy out at night taking some pictures. You being one of them, Steve being another. And you've had some great observations. Okay, we have David Levy, who is going to present some poetry to us. Welcome, David.
No, and we can't hear you.
Can't hear you, David. Have to unmute.
He is unmuted, but the microphone is not seeming to work.
Give it a kick.
Better?
No, we can hear you.
There you are.
And now we can't. Loose connection.
How's that?
There you go.
Is that better?
On again, off again, and buzzing, humming sounds.
Okay, let me just do the quotation.
Okay, we're good.
And you've just done a nice job with, you've just done a beautiful job with comets and how beautiful they might be. But in this quote, comets are considered dreadful. This is from Homer's The Iliad, not the translation from Chapman that became famous from John Keats, but a later translation from Alexander Pope. A peaceful guest, he saw Mycenae's towers. Armies, he asked, and armies had been given. Not we denied, but Jove forbade from heaven, while dreadful comets glaring from afar forewarned the horrors of the Theban war. I mean, I don't think comets are dreadful, but Pope did. So that's it for now. Thank you.
Thank you, David. Thanks for coming. I know you're a bit late, but thank you. That's excellent.
Try to be earlier next time.
Oh, excellent.
David, I was just wondering if you've ever tried Richmond Lattimore's verse translations of Homer.
No, not at the moment. I'm trying to concentrate between Chapman's and Pope's at the moment.
Okay. I'm not at all an expert.
It
but
seems like they're two different works completely.
Yeah. But I've read the one, Lattimore's done all three, the Iliad, the Odyssey, and the Aeneid. And they're the only ones I've read, but I found them just absolutely stunning. So I recommend them as a non-expert.
Oh, great. Me too. Thank you.
Okay, Rick, you have to write that up and put it in the newsletter so we know what we got to get. Okay. Thank you, David. Next, for a couple of updates, we have the science fair that's coming up virtually March 28th, and Bruce is looking for some judges. So please get a hold of Bruce. Or Bruce, do you have something to say about it?
Yeah, I was going to, thanks for mentioning that. Excuse me. Yeah, so at the moment, the general timing will be that sometime around the 1st of March, they will release an Excel sheet which lists all the projects and a little summary. And so then it's sent out to everybody, and so we'll get that, and we'll be looking to see which ones are relevant for our theme. And so then just check my my book here. Yeah. So we will about mid March, they'll be putting out they'll be putting out to the judges the projects. They won't be online directly, so we'll get a link to the internal sharing of the projects. And so then everything, as I say, is going to be online. So we will I'd be delighted if there were several people who would indicate an interest in working with me to go through the projects and pick out what's relevant, and then think about we then meet together to make a discussion and rating of the projects. So basically, we just simply have to say back. It's just giving them one name of the winner, and probably we will do. Last year we were given the opportunity to interview online. It's quite likely this time we will also not do it this year, and I mean just simply look at the projects and discuss it among ourselves, and maybe send some positive feedback back to the person we choose. So that's just a quick summary. And yeah, it was a lot of fun. And when we finally gave the award to the winners, it was a student. He's actually with his and his parents' permission, we were able to put his name and his project up on our own website, so you can actually look and see who it was. The project was really neat. It was about rockets, and as an experiment to figure out what the best kind of mix of fuel would be. Soda water, of course, but also the shape and the extension of the rocket, the design. So it was really quite neat. So yeah, I just wanted to share that. And several of the people I think are here tonight. Elena, you think you were involved? Graham, hey, you were involved last year. And I think 3 of us were the ones that had the fun doing that. So
Hey,
thanks.
that's great. Thank you, Bruce. And also Science Rendezvous is going to be a little different this year. It's going to be in May, but it's going to be a month-long event, and there'll be more information to follow. They're still trying to get some details on how we're actually going to be able to help out and run this year. So that being said, our next meeting is on March 9th at 7 p.m. and our guest speaker is Marcus Leach, Hunting FRBs on a Budget, the SIFT telescope. And so that should be interesting. He actually, I believe, has it set up on a piece of property up in Rideau Ferry. And that will be a very interesting conversation, because Marcus actually is on the Sarah radio list, and he actually gave some presentations to the BAA radio group as well. Every Wednesday, except the second Wednesday, which is our meeting night, we have our members' social Zoom time. It's sent out to the center chat list. So if you're not on our chat list, send a message and we'll get you hooked up. Check out our website. We're on Facebook. We are at Twitter. So send us some messages to Twitter at Astro Kingston and we shall forward it on. And check us out on the YouTube, on the RASC Kingston Center, and their past meetings are there and other Astro events. RASC handbooks, hopefully everybody has theirs now. And today I got Sky News, so hopefully everybody gets theirs soon. And if you're not, be patient. And as of this time, do we have any questions? If not, this is the official end of our meeting. So we will say goodbye to those people who are on YouTube.